So in subtopic 2.0, we're looking at the change in momentum. And if you recall, when we did our introduction to momentum, we said that there is description of motion and there's change in motion. So if there's any change in motion, that must mean that there is a change in velocity. So a change in momentum will occur anytime there is a change in motion. So let's look a little more closely at change in momentum. Well, the change in anything is always equal to that thing at any moment in time minus its initial. So we already saw that in our previous sheet of formulas. And we know change in momentum is a vector, momentum is a vector, initial momentum is a vector. Let's take a look at the units on this. Kilogram meters per second minus kilogram meters per second is going to give us units of kilogram meters per second. And you might say, well, why is that? Well, if I had 4 kilogram meters per second minus 3 kilogram meters per second, we have 1 kilogram meters per second. And so that's just a reminder when we are doing the dimensional analysis on a formula that there's no numbers involved. So we can see the change in momentum has the same units as momentum. That's not a big surprise. We had 3 versions of the change in momentum before. And remember that change in momentum from our formula lesson is a change in the product of mass and velocity. And the first of those can come about, and the most common that we will investigate has to do with a change in velocity. Well, that is mass times velocity minus initial velocity, and mass is kilograms, and any change in velocity is going to be result in meters per second for the same reason that we saw with change in momentum. The units remain the same, so the dimensional analysis on this version of the formula is also kilogram meters per second. And then if we are to look at change in momentum as delta m times v, well, any change in mass will result in kilogram units and meters per second as well. So that version of the formula yields the same units. And then lastly, we had a change in momentum that is due to both a change in mass and a change in velocity. Well, of course, then we see that is going to be kilogram meters per second again. And change in momentum is a vector just like momentum is. And that is because there is a change in velocity. A change in direction of the velocity means that there is a change in the direction of the momentum. And so therefore, change in momentum is a vector as well. So let's do a simple application of this. First, we'll start out with the situation. We've got a ball moving west, and it collides with a wall and bounces. So we've got an east-west situation. So we set up our coordinate frame. So we've got east positive and west negative, and it's moving westward. So we've got a ball moving westward. Like this, it's 1.000 kilograms, and it's moving westward at 6 meters per second. And since west is negative, that means that the velocity is minus 6. It collides with a wall. Well, if it hits a wall, the wall must be over here, like this. And so we can see there's going to be this moment of contact. And then after it bounces off the wall, it says it does so without a change in speed. So the speed is the same. And that means now that this has a velocity of positive 6 meters per second. So the speeds are the same, the directions are opposite. All right, and we know that this collision, there was something that lasted here for 0.20 seconds. Well, what is the momentum before the collision? That's a straightforward calculation. So P0 is mv. We've got 1 times 6 minus 6. So we have a momentum of minus 6.0 kilogram meters per second. And so our 6 had 2 significant digits. Our mass had 4, so we report 2. Okay, so that's our initial momentum. What is the momentum afterward? Well, the momentum afterward is going to be that same 1.00, but it's plus 6. So it is 6.0 kilogram meters per second. So that is the momentum after the collision. What is the change in momentum? There are two ways we could go about doing that. One is we could say, in the simplest sense, it's p minus p0. So that momentum of 6.0 minus a negative 6.0. And that means we have a change in momentum of 12 kilogram meters per second. Minus a negative makes it a positive, and so it's plus 12. And if we go back up to our drawing here, it makes sense. So let's see. For the momentum to change, it must first go to 0, and that's if it stopped. But then if it bounced off and moved toward the right, toward the positive direction, it needs to change yet again another 6 for a total of 12. Now we could have done this a little differently. We could have started out with our formula delta P equals m delta V, and then we have 1, and the change in velocity, let's see, it ended at 6 minus a negative 6. Oh, so that is 1 times 12, or 12 kilogram meters per second. And we want to do that double check, since the change in momentum is a vector quantity, that we check the direction to see that it is indeed plus 12. So there's two different routes we could take to determine that change in momentum. And then so the next question is, what is the rate of change in momentum? Well, the rate of change of anything is just that thing divided by time. So the rate of change of position, delta x, is delta x over delta t, and that has a name, velocity. The rate of change of position is this. The rate of change of velocity is that thing over time, and we know that's a quantity of acceleration. Well, the change in momentum then, delta p over delta t, is simply going to be that quantity. Let me just change the color here. The rate of change of momentum is delta p over delta t. So we have a delta p of 12, and the time is 0.20. And so that means that we have a change in momentum of 60. Two significant digits, two significant digits, two significant digits. We put a dot there indicating the 0 is significant. And now we've got the units. So we've got kilogram meters per second on top over seconds. So our final units then are kilogram meters per second squared. And that's 60 of them. 60 kilogram meters per second squared. Now at this point, a couple things should stand out to you when you see that and you see the units, is that kilograms are the units of mass, and meters per second squared are the units of acceleration. Oh, so we see that delta p over delta t is equal to the mass times the acceleration is experienced. So delta p over delta t is ma. What we come out with there. All right, so let's move on to our next part of this, which is to draw a momentum time graph of this encounter with the wall. So we have time, we have momentum, and we have 0. And we'll pull out our Oizerga. So the origin, we've specified where that is. The y-axis is momentum. Time, the intercepts. We're going to hold off on that because we're actually graphing it. We can read momentum and time. The gradient is delta p over delta t. Well, that's the rate of change in momentum. And we know that happens to be equal to ma. So delta p over delta t is ma. And the area is going to be momentum times time. And so let's see, if we did this as a formula, it's going to be mv times t. So kilogram meters per second times seconds is kilogram meters. And so it's kind of like mass delta x. That's an unknown quantity, but that is what it's equal to. All right, so now we've got our positive direction up here and our negative direction down here. And we ask ourselves, well, at the beginning, at time 0, what was the momentum? Well, we go back to our picture. Oh, we've got minus 6 meters per second, and that momentum was minus 6 kilogram meters per second. So we've got minus 6 kilogram meters per second. And it was minus 6 kilogram meters per second for a while until it hit the wall at this particular time. Now we know it hit the wall for a period of time of 0.2 seconds, and we'll call that delta t. That delta t is 0.20 seconds. And then we know afterward, after that period of time, it is plus 6 kilogram meters per second. And it remains so. So that's a graph at that point. Now, there must be a time when this ball reaches a speed of 0. Reaches a speed of 0. Okay, so yeah, that's probably in the midpoint. And so at the simplest level, we may say, well, this is what's going on with this graph, that it's a straight line. We could say it's a straight line. But we could also see that it might be like this. Or it could also be like this. The difference between the red and the green is that the red says that the rate of change of momentum starts out slow and then it gets much greater. It gets much greater and then it decreases again to 0. And the green graph says it starts out very, very large and then it reduces and then it increases again. Now, the first thing to notice when you look at this is what I would suggest is if you look around this point right here, the red seems like a more smooth, natural transition. But notice the function changes in a very drastic, immediate way. So it's like at the point of contact, the instant of contact, it is extreme. The effects are extreme. All right, and so we said that delta P over delta T is mass times acceleration. So that mass times acceleration, since the mass is constant, would have to be extremely large. So the acceleration is very large, and then it decreases and then increases again. Well, this is where we come into looking at our impact, what's going on with the impact, but also the videos of the balls that I had you look at with the tennis ball and so forth. Well, what we see then is that when the ball makes contact, when the ball makes first contact, it starts to compress. And then it compresses even more, and it gets to a maximum point of compression, and then it starts to expand again. So that point of velocity is when there's the maximum compression. So if you picture now taking a tennis ball and holding it in your hand and you squeeze it a little bit, a millimeter, not so hard. To squeeze it the next millimeter is harder still. And the next meter is even harder than that and harder than that and harder than that. So what that means is that the force required to squeeze that ball increases over time, which means it has a greater effect on the speed the more it's squeezed. And that is why the best way to represent this would be with the red. Starts out with very small effects. The ball is being distorted in a very small way, and then that gets larger and larger and larger and larger as it comes to a complete stop here at the midpoint, here where the velocity is 0. That's where we get the maximum compression. Then the ball starts to push it outward. The ball is compressed a huge amount, so it accelerates it outward very greatly. And as it expands outward, its outward force decreases and decreases and decreases until it's no longer in contact, at which point it's 0. And you notice then at that point that it's 0. So that's the graph of this particular collision, or as we might expect, any kind of collision. And to put another label in here, what we say here is that delta t is 0.20 seconds. So that's our momentum time. That's our momentum time graph. The next thing we want to do is to determine the change in momentum. Now, with our graph, with our picture that we had, we already know and calculated algebraically that the change in momentum is positive. our negative direction to the left and our positive direction to the right. So when we want to use vectors to add them, if we were to say, if we took p plus p0, all right, so p0 is, so here's our p, afterward we said was plus 6. And then we took the p0, which is minus 6. We can see then that the sum of the p's is 0. P plus p0 equals 0. But we don't want p plus p0. We want p minus p0. Well, really, when we're doing p plus p minus p0, what we're doing is we're adding the opposite of p0. So to find out delta p, we are going to take p and add to it a negative p0. So we'll start with our p vector, which was plus 6. And we already said that p0 is this direction. So the opposite of that is the opposite direction. So that is also, plus a negative 6. And so we can then see that the overall resultant is plus 12 kilogram meters per second. And so this is what we call vector subtraction. What we do is we sketch addition and then reverse direction for the second term, or the second vector. And that allows us to easily find that out, to find out the delta p. All right, so our last step here is we're going to consider the same scenario we had above, but now the ball is going to be covered in Velcro, which means it will stick to the wall. Plus and minus. So we know we have a p0 equal to minus 6 kilogram meters per second, and then the ball sticks. And so the p0, or the p afterward, is 0 kilogram meters per second. And it's, let's say it lasted for 20 seconds. What is the momentum before? So p0 is minus 6. We already calculated that previously. And afterward, we know our p is 0 kilogram meters per second. Change in momentum is going to be p minus p0, and p is 0 minus a minus 6 kilogram meters per second. So the change in momentum is plus 6.0 kilogram meters per second. Now, again, that's important because the momentum initially was negative, and for it to be 0 afterward, we have to have something occurring in the positive direction. The negative momentum decreased to 0, so that suggests then that the acceleration is positive. Now, if I would just point out that velocity in this case was negative, if we want to find the direction of the change in velocity, well, the direction of the change in velocity is, we imagine, the direction of a force causing it. Well, if this velocity goes to 0 upon impact, then that must mean that there is a force in the positive direction causing that to happen, causing a positive acceleration. So the change in momentum is positive 6. And then the rate of change of momentum, we have delta p over delta t is 6.0 divided by 0.2. And so that is going to be 30 kilogram meters per second squared. And we need two significant digits, so we put the dot there. So 30 kilogram meters per second squared. So comparing that to the previous, if we compare that to the previous one was 60 kilogram meters per second squared. So what we had was, we had half the change in momentum, because the first change in momentum was 12. And so from the previous, we had 12 over 0.2, which was 60 kilogram meters per second squared. And so we could see then that the rate of change in momentum must be greater, because the total change, which was twice as large, occurred in the same amount of time. So we would expect twice the rate of change of momentum. And that concludes our introduction to the change in momentum. In our next installment, we will take a look at impulse and systems thinking.